Hi, I'm Dr. Andrew Bernard from Michigan Tech University, and I'm here today at PCB Piezotronics to give you a demonstration on acoustic directivity. The first thing we'll be doing is talking a little bit about the theory. So there's two metrics required to fully define an acoustic source. It's sound power level and its directivity. Today we'll be talking about directivity. The directivity factor is the ratio of the squared pressure of the source at some angle to the squared sound pressure generated from a monopole or omnidirectional source with the same sound power level as the given source. And that's the equation you see right here. The directivity index, noted DI on the slide, is simply 10 times the base 10 logarithm of the directivity factor, Q sub D. The directivity of the source tells us over which angles the source will radiate its highest sound pressure. Directivity can be measured by rotating the source and using a fixed microphone position, or, as we'll demonstrate here, using a fixed source and a rotating microphone around it. Here we have a PCB Model 378 BO2 half-inch free field condenser microphone that's fixed to a rotating boom arm. The boom arm is pivoted around a rotary potentiometer, and that provides the angular position feedback for the directivity measurement. For our data acquisition system, we're using a compact DAC chassis with 3 channels of data. The first is the sound pressure, the second is the potentiometer input voltage, and the third is the potentiometer feedback voltage. Finally, we're using a 2-channel speaker module as our source. As I move the boom arm around the arc, the sound pressure level will plot as a function of angle in real time. This type of polar plot is common in directivity measurements, and although you won't see it here, it's oftentimes normalized to 0 dB at 0 degrees for simplicity. We're assuming the source is linear, so we can infer that the directivity is not a function of on-axis sound pressure level. In other words, no matter how loud I play the source, the speaker in this case, the shape of the directivity curve won't change. When we measure directivity, we like to do it in a venue that doesn't have any reflections or contaminating noise sources. That's why we typically use an anechoic chamber, like this one in the anechoic chamber at PCB headquarters. We'll start out running the 2-channel loudspeaker at 300 Hertz, and we should see a nice omnidirectional beam pattern. And you can see very clearly one large beam at 300 Hertz. Now we'll increase the frequency to 1 kilohertz. And we'll do the measurement again, and what we should see this time is 3 lobes and 2 notches in the directivity pattern. So there's the first notch. And there's the second notch. And you'll notice that the 2 notches are symmetric about the beam angle. In conclusion, when we measure directivity, we need to make sure there are no reflections or background noises present to contaminate our measurement. That's why, when we make this measurement, we typically use an anechoic chamber. So knowing the directivity of a source can be very helpful when you're placing sources, either for a sound enhancement system or if you're trying to do sound level minimization, like when you're orienting machines on large factory floors. That's all we have for this demo. I hope you found it informative, and we'll see you next time.
For more information, visit PCB.com or give us a call at 1-800-828-8840.